Good job. Okay, next. Let's see measurement of length. In this unit, you have to show an understanding of how the sizes of objects, such as an atom and the Earth, can range in orders of magnitude, and also describe to measure the variety of lengths using the appropriate instruments, such as tape measure, meter rule, vernier calipers, micrometer, screw gauge. Let's recall some of these one first. Okay, length is one of the 7 base quantities. See, okay, we are using the meters, okay, to count it. Yeah, tape meter. Okay, what do we use? Okay, let's see what are the sizes. Let's see the orders of magnitudes of sizes. We can see there are the smallest and also the biggest in this picture. Where do you think is the smallest, and where do you think which one do you think is the biggest? Is it this one or that one? Yes, that's good. So actually, this one, the 10 to the power of minus 16 is actually the smallest, yeah, because that is minus 16. Meanwhile, the below one is the 10 power to the power of 2, yeah, or 10 squared. That is 100 meter is the length of a football field. Okay, and then we can see that is for 10 to the power of minus 16, radius of hydrogen nucleus, and then 10 to the power of minus 10 is the size of a typical atom. Let's see the bigger now. Just now we have ended, from the previous slide until 10 squared. Now we're going to see which one is even bigger. Okay, you can see that at the 10 to the power of 4, that is the height of the Mount Everest. You see at 8,848 meter. And then you can see the 10 to the power of 6, that is 6,378,000 meter. That is the radius of the Earth. And if we go forward to the 10 to the power of 16, we can find the 9, or what is that? Well, yeah, 9.5 to the power of times 10 to the power of 16 is the distance traveled by light in 1 year. Okay, you can imagine so big. Okay, but the biggest one is still 10. Okay, to the power of 22. So it is 2 times 10 to the power of 22 is the distance from the Earth to the Andromeda galaxy. So if you study later about physics, you will find some good and nice information, of course, about astronomy, which will be very interesting. Let's continue. Now we are going to continue to IT activity, what we are going to do. The objective is to see animated pictures of common biological and technological objects microscopically. The instruction is to click to take a trip into the nano world. Welcome aboard. Okay, later you can try. Yeah, welcome aboard to the trip. Okay, but we are not going to discuss that here because it will take a very long time. And at every step or every stage, click on the expanding rectangle to magnify the spot and take a closer look at the structures in each new unexplored territory. Let's continue. In this slide, we are going to study about the measuring instruments. There are 4 that we are going to study in this slide. The first is the tape measure that is very common that we use, especially used by the construction worker. Meanwhile, for the meter rule, we use this to count, for example, also like to measure everything that is flat, like for example, like the width of tabletops, and it is in centimeters. Meanwhile, the tape measure can be a few meters. And then the vernier calipers, counting for a few centimeters, even smaller. Okay, for example, the thickness of a laptop. And the next one is the micrometer screw gauge. That is a few millimeters, for example, the thickness of a coin. You can visit our science lab to do experiments for using these instruments because we have all the complete facilities to do it. So don't forget to ask your teacher. Now, precision of an instrument. The precision of an instrument is the smallest unit that the instrument can measure. For example, consider a meter rule. We can see here that it is counted by centimeter, but also there are lines to show the meter. So we can say that the smallest difference in measurement made by the meter rule is 0.1 centimeter or 1 millimeter. Yeah, we can see because it can count until the smallest to the millimeter. We can see it from the meter rule. Now, what about measuring accurately with the meter rule? So we have to remember some of these things. We have to avoid parallax errors. Parallax errors are a common thing that happen to us as scientists or observers, because when we measure or when we see something, okay, we are not putting our eyes, yeah, in perpendicular uh, position. So that makes us judge or count the number or the measurement incorrectly. So for example, when we say accurate length of object 2.9 minus 1.0 is 1.9 centimeter. Because why? We have the possible zero error at this end. Okay, so we can start counting from number one. As you can see, when you have a ruler in the class or the meter rule, sometimes your meter rule will be shaped like this. Yeah, it is not straight. So it will create or it will make the parallax error becomes possible. So we have to move away the object and then count it from 1 up to the next point, and then we minus to 1. 2.9 minus 1.0 becomes 1.9. And then you can see the eye. Okay, the eye must be positioned right above or perpendicular to the object. Don't see it from, for example, the corner of to the left or the corner to the right. So it will give you a parallax error. Okay, this is the example. Because why? If we see it from the left or from the right, not perpendicular, you can see that we will measure it by 0.9 and this one by 3. Okay, so when we count with this kind of position, that means you will have the wrong measurement. 3.0 minus 0.9 is 2.1 centimeter. And then the next one is we have to reduce random error. Why? Because when we try to measure something, okay, every different action will sometimes give you a different result, especially when you count very small objects using the micrometer or maybe the vernier caliper. So it is better for you to repeat the measurement and take the average value of the measurements. And then not only that, don't forget to correct any zero error. Okay, so like just now I've told you, you have to be careful. Make sure that the 0 centimeter mark on the ruler must not be exactly at the end of the ruler, because it will create the zero error. Okay, so if it is located at the end of at the end of the ruler or the beginning of the ruler, that means you have to avoid using it, because not only the shape might not be straight or in a good square manner, but also it is because the wear and tear may make it unsuitable for measuring purposes. What about tape measure? Tape measure precision is 0.1 centimeter or 1 millimeter, measuring a length of several meters and measuring the length of the curve. Okay, and then when we have reasons for use, okay, because if you see the tape measure, it is longer, but still you can count it per centimeter, and there is the meter, millimeter available on the tape measure. So reasons for use, it has a range of a few meters and it is flexible. So when you are measuring the non-flat objects, like the distance from one side of a room to the other side of the room, you can also use the tape measure. Okay, but remember, you have to ensure that the tape is not slack or twisted, because if it is twisted or maybe it is not straight anymore or if it is slack, that means it will change or it will influence the counting of the meter. And not only that, when you are not pulling it side by side in an evenly manner, so it is not straight, for example, it is bent, that means you will get not accurate result. Next, about vernier calipers. If you see the vernier calipers, you can see that you will put the objects on these two sides, you see, okay, on these two sides, okay, and then you will move the jaws, yeah, inside jaws, to measure the internal diameter of an object, okay. And not only that, you can also check from the main scale, yeah, by sliding the vernier scale, okay, and then a small sliding scale alongside the main scale that allows us to read a fraction of the smallest interval. And also we have the outside jaws used to measure the external diameter or width of an object. Again, it is difficult for you to understand thoroughly if you do not do it in practical. So you have to do it in the science lab with your science teacher. Okay, I have explained to you just now. For example, we have a ball. The ball do not have any straight line, okay, on the each side of the ball. So for example, we are counting it, then we have to put the jaws right to the left and to the right of the object. We have to put it inside or outside the jaws. Okay. So step one, you put the grip the ball bearing gently using the outside jaws. Okay, and then you can count this one. You see. Okay. Step two, read the main scale to the immediate left. Okay, immediate left. Okay, this one. See which one that it falls. Okay, that means it is 3.1. Okay, you can see. Okay, 3.1 in step 2. And then you can also see step 3 when the line, okay, coincides, yeah, where is the mark finally coinciding with the marking on the main scale. So you can see the writing 1, 2, 3, 4. Okay, so that means it is 4 right after the step 2. Okay, 1, 2, 3, 4. So we got a 0.04 centimeter or 0.4 millimeter. So by that case, we will count by adding the main scale just now, the first counting in step 2, and we plus step 3, you got 3.14 centimeter. Okay, hopefully you have understood that. Okay, next question. What is the precision of a pair of vernier calipers? Still remember just now? Yes, let's see the answer. Good, because just now we can even count until the last, okay? So after the 0.1, so 0.01 centimeter, okay? So the answer will be 0.01 centimeter. What about the accuracy and zero error? For the reading to be accurate, there should be no zero error. The two zero marks on the main scale and the vernier scale must form a straight line as shown in the diagram below. Okay, so make sure that this happens. Okay, when the jaws are completely closed. Okay, so the two zero marks, the zero here, and then this one should coincide. So if you have this, that means there will be no zero error. Now, how do you correct zero errors? Should a zero error exist, correcting the error gives the accurate corrected reading. See, for example, if we have the positive zero error, okay, because this one, the first one does not coincide, okay, and then also negative, but because we see the first zero on the downwards, okay, it is going to the right, slightly to the right, we have a positive zero error, but downwards we have the zero downwards, okay, zero mark of the vernier scale is slightly to the left of the main scale, so you have the negative zero error. So when it happens, you can have the correction, okay? So we see here, when should we have the correction? 3.17, okay, we minus, because see, remember positive, zero error, okay? So we count, that is plus 0.03, okay? Remember, still remember, hopefully? Okay, that's good. Okay, next. We see this one, the next one. We have minus, okay? Minus because we have negative zero error. So 3.11, okay, this one, 3.17. Okay, we get it from the right side, remember? Okay, and then we have to minus 0.03. Okay, so that makes us having 3.11 minus 0.03. So we have 3.14 centimeter. Okay, hopefully you have understood about this one. Okay, next. Let's do the exercise about the zero error. Okay, what are the zero errors for this vernier calipers? If you see the picture on the left, you see that the number 0, okay, for the vernier scale downwards is on the right or on the left of the main scale? On the right, that's good. So if it is on the right of the main scale, so it should be positive, positive zero error. And then if you see the first time the marks coincides, Yeah, because if it is positive, we count it from the left. If it is negative, we count it from the right. Okay, I repeat, if it is positive, we count it from the left. If it is negative, we count it from the right. So because this is positive, we count it from the left side. Okay, from 0 to 1, that is finally coincide. So how many steps it is? 1. Good job. So that means the positive zero error is positive 0.01. Good job. Now, number 2. Okay, the number 2, you see the vernier scale, the 0 of the vernier scale is on the left of the 0 of the main scale, of the top. So that means we have what we call negative 0 error. If we have negative 0 error, we count it from the back. Okay, you see from the 0 on the right, go to the 8, how many steps? Yes, 0 to 9, 1, 9 to 8, 2. So we have 2 because it is negative 0 error, so we have minus 0.02. Okay, hopefully understand. We will talk about the IT activity for groups. The objective is to improve your competencies in reading the vernier calipers. You can also do this with your friends during the science lab. Okay, you can also watch this video first, and then don't forget to click and drag to part the jaws a certain distance apart. Okay, and then determine the reading before checking against the given answer. Repeat for 4, 5 or more different readings. Remember, we have to count it several times and then count for the average for more accurate reading. See another example of how to count the 0 error in the vernier calipers. Okay, we can see before the vernier calipers is being used, you see that the 0 downwards, okay, the 0 downwards is actually on the left side of the main scale. So which means we have negative 0 error, okay, negative 0 error. And then because it is negative 0 error, we have to count it from the right side. If we count it from the right side, that means we have to count from the 0 at the right side. Okay, and then we see which mark, the first that coincides with the main scale on the top. We see that it is number 9. So 0 to 9, there is only one step. So we have what we call negative 0 error of minus 0.01. Okay, now let's see the next example. Not the next example. Now after we put the object, now we put the object inside the jaws. Okay, now you see that we have 1.1. Okay, the first time the 0 starts of the vernier scale is after 1.1. So we have a 1.1. After that, we count again. Which mark of the vernier scale first coincide with the marks of the main scale? Yes, it is 4. So we have 1.14. Okay, that is the reading of the vernier calipers, 1.14. Okay, and then we see that we have the negative 0 error of minus 0.01. So how do we count? So we count it by correcting the reading, by observed reading minus 0 error, 1.14 minus 0.01 centimeter. So we have 1.14 plus 0.01. We have 1.15 centimeter. Okay. To study how to measure the length using the micrometer screw gauge. Okay, for this one, we are going to have the precision up to approximately 0.001 centimeter. And then the usage of the micrometer screw gauge is to measure very short lengths, such as the diameters of wires or ball bearings. Okay. Now, reason for use, because it can provide a precision of approximately 0.001 centimeter for small measurements that fall within a suitable range. The following diagram shows the labeled parts of a micrometer screw gauge. Okay, if you see, the left side is called anvil, okay, and then spindle, okay, to push the object forward and closer. And then we have a cross section of wire. Okay, and then we have the lock lever. My main scale is located in the middle. Okay, and then there is a thimble scale that we will move to measure it, and then thimble. Okay, and then ratchet. Okay, how to use the micrometer screw gauge. Okay, we see Like previously, we will call it the main scale, and then we will see from the main scale first. We will check the datum line. Okay, for example, we have to turn the thimble until the anvil and spindle touch the object, and then turn the ratchet until it clicks. Okay, clicks in place, so we know that it's stuck. Okay, next, we can see that the main scale reading, okay, you see the first 0, 1, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, the first time it stops at 8, okay, and then we can see the next one before going to the next part is 8.5, okay, 8.5 millimeter, okay. You can see. Okay, next. The first time, I hope you can see what I'm saying here. So after 6, 7, 8, okay, 5, 6, 7, 8, you can see then it stops. It doesn't go to the next one. Okay, that is main scale reading until 8. Okay, 0.5. Okay, after that, we can see from the thimble stops until 0.4. Okay, 0.40 millimeter. Okay. Okay, hopefully you can see that too. Okay. Now, from that, we can totally main scale reading plus the thimble scale reading. We have 8.5 millimeter plus 0.40 millimeter. So we have 8.9 millimeter. Okay. Let's see another example so you will understand better. See another example. Okay, what is the precision of the micrometer screw gauge? Okay, we can see to the right side, we can see that after 5, 6, 7, 8 again, 8, and then you see the datum line. Okay, it is above 0.4, so we got 0.5, so that is 8.5, and then the thimble stop at number 0.40. You can see the writing from the thimble, it's 0.40. So if we plus 8.90, okay, 8.5 plus 0.40 millimeter, you have 8.90 millimeter. Let's go to the next part about zero error. So we have studied about zero error in the vernier calipers, and now it's time for us to understand the zero error for the screw gauge. Okay, let's see. When we have the anvil touches the spindle as shown below. Okay, we can see the anvil and spindle when it touches closely, and then we have a zero that is in straight line. So it means there is no error, okay, because it's exactly at 0.00 meter. Okay, if it is not coinciding, that means it has zero error. Let's see. Okay, the smallest reading is 0.00 millimeter. Okay, so if the zero and the zero from the datum line coincides, we do not have any zero error. Okay, what about the below part? We see that the zero and the zero down the top from the datum and the thimble does not coincide. And then the zero is located downwards. That means inside the zero or below the zero. So that means we have positive zero error. Okay, if we have positive zero error, as the previous example, we will count from the zero to the top. And then we can see that there is how many sides of that to that one? Okay, 1, 2, and 3. Good. So we have the zero error of plus 0.03 millimeter. In that case, we have to minus. Okay, minus 0.03. So 8.93 minus plus 0.03. So we have 8.90 millimeter. Okay, now the next one. Now we see that the zero marking, okay, we have is above the zero, which means it doesn't touch the zero yet. So we have a negative zero error. Then we can also see how many is that. So we count from downwards, remember? okay, from downwards. So we count, it is how many? 1 and 2 and 3, yes. So it is minus 0.03 for the negative zero error. Okay, if we see the right side, we got a reading of 8, okay, 8.87 because it is more than zero point 0.5, right? More than 0.5 plus 37. Okay, so 50 plus 37, we have 8.87. After that, we have negative zero error, so minus 0.3. So we have 8.90 millimeter. Okay. Let's do the worked example. The diameter of a wire is measured using a micrometer screw gauge. A student takes an initial zero reading and then a reading of the diameter. What is the corrected diameter of the wire in millimeter? Okay, if we see the picture from the thimble, the zero lies does not coincide and it is above the zero, okay, of the datum. So that means we have what? Negative or positive zero error? Yes, good. Negative zero error. Okay, we have negative zero error. So we are going to count from downwards, and that is 1, 2, 3, and we see, yes, 1, 2, 3, 4, 5, 6. Okay, good. From the 40, okay, we go up. So we got 6, okay, minus 0.06. Okay, and then we have on the right side we have the reading. Okay, 5 stops exactly. Okay, the datum falls on 5, and then we count from the thimble, we have 45, and then 2 more lines, we get 47. Okay, so we have 5.47, okay, for the reading. And then the actual length, because we have a negative zero error, 5.47 minus 0.06. So we have 5.53. Okay. You can do the IT activity in pair by browsing the URL below. Okay, don't forget to take turns. I have another questions to test your ability in understanding this exercise. You can see the left one is the reading of the micrometer screw gauge when the jaws are closed, and then the right side when the object is placed between the jaws. You can see the number 0 of the symbol lies below the 0 of the datum line. So that means, yes, good. It is the positive 0 error. So the positive 0 error, if you see the 0 to the datum line, there are 2 steps. So that means it is 0.02, positive 0.02. Okay, let's see the right side. The right side, we can see how many is that? How many centimeter? Oh, sorry, millimeter. Okay, 0 millimeter, 1, 2, 3, 4. Good, 4 millimeter. And then you can see that it has reached the 0.5. So you have 4.5. Okay, and then you count from the thimble. 30, 31, 32, 33, and 34 because it is below 35. So you have a 4.5 millimeter plus 0.34 millimeter. So you have the reading, okay, the reading of the micrometer screw gauge is 4.84 millimeter. And then after you correct it using the zero error, yeah, you minus the observed reading of 4.84 millimeter minus plus 0.02 millimeter, you have, yes, good, 4.82 millimeter. Very good job. Okay, let's go to the next. We will start practicing the question on, again, vernier calipers, but this time we will assume there is no zero error. And what is the radius of the cylinder? Let's see. But also for B, state another precaution you can take to minimize other errors. Okay, if we see the picture here, as usual, we must understand which one we call the main scale. Which one is the main scale? Yes, good. Yeah, this one we call it main scale. Okay. And then this one is the This one, okay, is the vernier scale. You can see the first 0 falls here. So 1, 2, 3. Okay, it stopped here. So you have 0.3 centimeter. Okay, and then we will check now for the millimeter. Okay, let's see if you see this one. Okay, and then you see again here is, are we seeing the lines that coincide? I think not this one, no. Okay, 2, no, 3, no, 4, no, 5, no, but 6, this one coincide? Yes, this one. So we have 0.3 centimeter. Okay, and then plus, see this one in millimeter, so 0.06 centimeter. Okay, so if we add this one, 0.3 centimeter plus 0.06, we have 0.36 centimeter. Okay, I hope this one is clear for you. Let's see another example. Maybe before I forgot, for the previous slide, remember that to make sure that we have the correct reading, we can minimize the error by doing many measurements, yeah, more than just one. So we have, what is that, average. The average will, what is that, make sure that we have better accuracy. So understanding how the vernier scale gives a reading of up to 0.01 centimeter will also raise the level of skill of you from knowledge to able to master and really understand about vernier calipers. Now, how do we prove that precision of a pair of vernier calipers is 0.01 centimeter? Okay, let's see one more time from the example. Yeah, this is the main scale. Okay, the main scale is 0.1. Okay, when finally the 0 is lying here. Okay, you can see that it happens that the vernier scale, okay, vernier scale does not fall after 1. So it is below 0.1 centimeter. Okay, you can see here. Okay, now, which means right now we do not have more than 0.1 centimeter. It is below. Okay, each division on the main and vernier scale is 0.1 centimeter and 0.09 centimeter respectively. So we have a difference of 0.01 centimeter. As the movable, okay, see, because we put like this, okay, the first time it coincides, okay, so that means we have what we call, okay, 0.1 centimeter, exactly at 0.1 centimeter. Okay, and then also as the movable jaw slides, the vernier scale reading changes by a minimum of 1 division, which results in the reading changing by a minimum absolute value of 0.01 centimeter. So remember, whenever we want to move it, we have to at least get a 0.01 centimeter.